Wonderful. All right, welcome back. So today we begin part three. Well, now we begin part three, still today, uh, in which we will explore applications of the vortex formula to optimization. And let's go ahead and just see some examples. Let's recall the vortex formula. The vortex formula says the vortex of y equals ax squared plus bx plus c is at x equals negative b over 2a, and it maximizes if a is less than 0 and minimizes. I said minimizes, but spelling is really hard if a is bigger than 0. I think that's better. All right, so let's see this in application. So here's an example. In order to keep price, you have a secret. You're going to keep that secret by burying that secret. So you find a little spot in the desert, you bury it right there. In order to keep people from just stumbling upon your burial spot with some sort of shovel, you decide, well, you know what? I'm going to put fences around like a big piece of land that contains it. So that'll dissuade people from coming onto the territory. But if you fence it in like too tight, it'll be too obvious where it is. So here's what you'd like to do. You have 1,000 feet of fencing, and you'd like to capture some area. More area is better. The bigger the area, the more safe your secret is in the desert. And you're doing it on a bit of land where there's this cliff wall in order to keep, yeah. So you don't need to fence the side of the cliff because you can assume that no one's going to like climb up the cliff wall. If they were going to do that, they'd just climb your fence anyway. So you don't need to bother fencing in the cliff wall. So with those 1,000 feet of fencing, what's the maximum area you can enclose? So here's the strategy. Let's build a model that talks about the length of fencing we use and the area enclosed. So I guess let's make up some variable names. Let's call this length L. It's going to be a rectangular region, so these two regions will be the same. And let's call this length D. Well, then we can write down some relevant things. So 1,000 feet is equal to, and you know what, I'm going to suppress all the units. All the units will be in feet. Equals length of fence. But by looking at this picture, we can see exactly how much fencing we've used. Equals 2L plus D. It looks like we could solve for one of the two variables. I think D looks easier to solve for than L. D is equal to 1,000 feet minus 2 times L. All right, that feels pretty good. All right, so let's use the area formula. The area of this rectangle is length times depth, but I have a formula for depth, so that's L times 1,000 minus 2L, parentheses are important, equals negative 2L squared plus 1,000 L. And I want to maximize this. This is where the vortex formula comes up. This sucker right here, this looks like a degree 2 polynomial, a quadratic function. Sorry, I'm using fancier words when I have a different word. Also known as a quadratic function. Vortex formula maximize or minimize? Well, let's see. It looks like here's the value of A. There's the thing in front of the square term. It maximizes if that is negative, minimizes if it's positive. It's negative. Negative 2 is negative. So the vortex maximizes. And by the vortex formula, this vortex is at, well, the vortex formula is phrased in terms of x, but, you know, whatever the independent variable is, here it looks like it's L. By the vortex formula, L equals negative B over 2A. That's negative 1,000 over 2 times negative 2. Let's see. The negatives cancel. That's 1,000. No reason to switch colors right there. 1,000 over 4, also known as 250 feet. So the optimum choice of L is 250 feet. Let's now answer the original question. So you have 1,000 feet of fencing. You must capture a rectangular region. How large an area can you capture? So L equals 250 feet. Maximizes area, but that doesn't answer the question. I actually want to know what the area is. The max area is what happens when you plug L equal to 250 into this. And you know what? I think this looks easier to plug 250 into. The maximum area is 250 times 1,000 minus 2 times 250. So this is equal to that, so I could use either one. All right, and let's evaluate that, I guess. This is 500. 1,000 minus 500 is 500. That's 250 times 500 square feet, also known as, let's see, 25 times 5, 5 times 5 is 25. Carry the 2, 5 times 2 is 10. 125. So it's 125 with an extra 3 zeros. So it's 125,000 square feet. Feel pretty good? Cool. All right, carrying on. So generally in class, I would say I want you to do this next one. And there's like a trick in this one because the units aren't consistent. But given that thing about the units, I'll say you should do it. Pause the video for a second, come back. And now that you're back, let's talk through this. So, Marble League High Jump World Record is currently held by a marble named Mandarin of Team O'Rangers. Here is the record-breaking jump. Mandarin leaves the ramp with an initial velocity of 285 centimeters per second. So here's the initial velocity times time. The flight of this marble over time is given by this initial velocity term, and that term given by gravity. At what time will Mandarin achieve its maximum height? Well, the first thing to notice is some of this seems to be conveyed in centimeters, some of it seems to be conveyed in meters. We should probably just pick one set of units and walk with it. In order to do that, I guess I'll pick centimeters as the units I'll walk in for distance. So let's just convert that 5 meters to, well, what's 1 meter? It's 100 centimeters. That's what a centimeter means, 1/100th of a meter. So whenever you need to convert units, there's how you do it. You multiply by something that is equal to 1. 100 centimeters is 1 meter. All right, so it looks like h of t is 285 centimeters per second. You know what, let's subtract units now that we have it. Equals 285 t minus 500 t squared, t in seconds, h in centimeters. All right, so let's look at that. This is now a quadratic function. Let's find the vortex. The vortex, well, that's negative, so the vortex maximizes. And the vortex is at t equal to negative b over 2a. So that's negative 285 divided by 1,000. Oh, and I lost a negative sign. Right, that 500 was negative, which is important because the negative signs will now cancel. And division by 1,000 is easy, right? You just, for every decimal place in the denominator, you move the digit over one. Equals 0.285 seconds. So we know what time the vortex occurs. The vortex, so at t equals 0.285 seconds, the marble is at its maximum height. All right, so let's just make sure that we've addressed the problem. So there's a when will mandarin achieve their maximum height? We just found that. That's this. What is the maximum height? Well, let's answer that next. To get the maximum height, plug in 0.285 in seconds. But this formula is for time measured in seconds, so we can just use it. H of 0.285 is equal to 285 times 0.285. And don't worry, I won't do this evaluation by hand. Minus 500 times 0.285 squared. So what'll I do? No, I won't do it that way. I'm going to pull up. You can't see what I'm doing, but I am currently pulling up my preferred calculator. 285 multiplied by 0.285 minus 500 times 0.285 squared is 40.6125. Centimeters. All right, so I guess there's a follow-up question. So there's the maximum height. The previous record holder was 38 meters. This does in fact break the record. And in fact, it does so by, I don't want to do the subtraction, about 1.4 centimeters. Right, you have to do subtraction to do that. Oh no, I did the subtraction wrong. 2.6 centimeters. Cool, that feel pretty good? Nice. So there's one last problem to think through. And again, this was going to be an exit quiz kind of thing. So in class, I would ask you this question. I'd say, once you have the answer, show me the right answer, and then you can leave. So do the same thing. Get an answer, find it. Great, you've got it. Let's talk through it. So if you want to, let's read the problem now. The revenue which at Once gains from the sale of needs, which, as you know, are a thing which everyone needs, is modeled by this function. The revenue at any set price is equal to negative 1/2 the price squared plus 1900p, where p is the price, the sale price of one need. Where should the Once set the price in order to maximize revenue? Well, this is obviously another maximization problem. It has the word maximize in it. So it looks like we want to maximize, so let's find the vortex. So the vortex is at p, the independent variable, equal to negative b over 2a. That's negative 1900 divided by 2 times -1/2. It looks like some stuff simplifies. 2 times 2 divided by 2, those cancel. Negative in the numerator, negative in the denominator, those cancel. Is equal to 1900 and unfortunately the lifting of the lower x doesn't actually specify a currency, does it? So that's it's the best we can do. It's 1900 whatever's maximize the formula. Now one could maximize now by plugging in RP, but read the problem. Does the problem ask you to actually say what the maximum revenue is? It doesn't. So here is the answer. It just wants the price that maximizes revenue. This is the price. All righty. Wonderful. Sorry for getting this up so late. See you in class. Ciao. That button.